Today on this episode of The Crossover, we will be discussing the NASA DART mission, Double Asteroid Redirection Test, with NASA Science Directorate Dr. Thomas Zerbukin. Learn how NASA is preparing to save the human race with its planetary defense system in the event of a cataclysmic asteroid collision. Much more on this episode of The Crossover. Good afternoon, everyone. I'm going to be talking with Dr. Thomas Zerbukin about the NASA DART mission. There he is. Hold on. Hey, Thomas, how you doing?
Doing well. Sorry, one of my microphones apparently was spun, so it's all good. Yeah, how are you doing?
I'm all right. Listen, thanks for joining us. Super excited to have you back on the podcast, and I'm going to do a brief introduction just while everyone's logging on here. We have the pleasure of speaking with my friend and colleague, Dr. Thomas Zerbukin. He is NASA Associate Administrator and Science Mission Directorate. He earned his doctorate and Master's of Science with a degree in physics from the University of Bern in Switzerland. Prior to joining NASA, Dr. Zurbuchen was a professor of space science and aerospace engineering at the University of Michigan. He was the founding director of Michigan Center for Entrepreneurship at the College of Engineering and developed several innovation initiatives, one of which led to the top-ranked Entrepreneurship program nationally. On a daily basis, Dr. Zurbuchen works to ensure that NASA's science missions build partnerships across disciplines, and during his career, he has authored over 200 peer-reviewed articles. His honors are multiple and include NASA Ground Achievement Awards, induction as a member of the International Academy of Astronautics and the Swiss Academy of Engineering Sciences. He's here today to discuss the DART mission, Double Asteroid Redirection Test, which is just a phenomenal mission. I really want to delve into where it started, how it came about, and what the results are. So again, thanks for joining us again, Thomas. Great to have you on.
So glad to be on, and thanks for doing this.
Well, let's just start with kind of the basics. How did the idea of this DART mission first arise, and how long has it been in the making?
So first and foremost, if you ask the American people, what are the most important things we should be doing as an agency? There are two that consistently go to the top. The first one is protect life on Earth by weather forecasts, focusing on our planet. And the second one is this one, planetary defense, as we call it. Really protect the Earth from impact from this. And the Congress is listening to the American people. And in 2005, they came up with a law that basically directed us that we need to find 90% of the objects of the type that we hit with DART or larger, 140 meters, 460 feet or so or larger. And we should do that. Frankly, when I went to NASA, the first thing I did in 2016 in the first budget is really focus on that much more so to kind of both achieve that goal, but also to really move us down this. And so in 2017, which was my first year I was there and I had influence in the budget, we actually included that into the budget and then confirmed to move forward. It launched, of course, day before Thanksgiving last year.
Now tell us a little bit, when was the last consequential asteroid to hit the planet?
Well, we had a kind of a 1 in 100-year event in 2013 in Russia, where an asteroid kind of the size of a small building came in, and you've seen the movie Chelyabinsk, you came in, Chelyabinsk, it came in and basically flattened a lot of force, kind of by a miracle almost. Nobody was killed by it. And again, this is the size of a small building. It's a lot smaller than what we hit with DART, which is the size of a pyramid, right? Many of the objects that we've observed that are, maybe a kilometer across, so 10 times a football field, kind of across the whole thing. So that's the most recent one. Of course, the Earth is scarred of impacts, and what many people miss is that every day, in fact, 80 to 100 tons of material fall down, kind of smaller stuff, right? So we're taking a bath as a planet in dust and rocks. It's just the ones that we should worry about, are the ones that became a problem for the dinosaurs are bigger, kind of if you want the size of a football field, kind of a stadium, or all the way to 10 kilometers, 6 miles across, right? Kind of those are the ones, kind of the 6 milers are the ones that really changed life on Earth in a substantial fashion as the dinosaurs experienced.
So it would only take an asteroid the size of a football field to end life on Earth?
The size of a football field would really be a local catastrophe scale. So kind of if a size of a football field kind of came down, including the one that we hit, Dimorphos, right? Kind of the small body, the one that we hit, if it hit Washington, D.C., it would basically be the equivalent of not only one, but multiple nuclear bombs into Washington, D.C. So it would have a local catastrophe scale. The size of 6 miles across would, over years, change all of Earth. It would create depending on when it goes down, matters where you hit. But the one that hit in Mexico there in the water created a worldwide tsunami, wiped out a lot of life right in the first hours, but then changed the atmosphere so much that it took years to recover. So animals that required sunlight kind of to a large extent to survive, frankly, did not have the same kind of sunlight. And so it really, depending on the characteristics of life, is fundamentally life-changing.
Now, how do you guys at NASA, how do you survey what's coming towards the Earth? And do you have any special equipment in particular that's dedicated towards detecting these potential catastrophic asteroids?
So the Planetary Defense Program is using both space-based and also ground-based observatories for that. So the ground-based ones in Mount Haleakala, on Maui, there's 2 telescopes that scan the sky every night. Per night, we may discover 3 to 4 bodies, kind of small bodies from, small near-Earth objects that we had not seen before. Those are the ones we've discovered. Something like 10,000 of those. There's another, we believe, based on models, 15,000 we haven't found yet at that scale. We found basically of the objects that are near us that are a kilometer or higher, right? We found most of them, well over 90%. So it's really those. So again, we looked at ground-based. It's not just us. It's also other agencies that look at it in Australia, South Africa, and so forth. We look from the Earth. We have one asset right now in space that has been repurposed to really look from space. But what we really need to do to kind of achieve the goal that the Congress gave us, and then also find objects that are very dark, in the sky or in specific orbits that we can't see from Earth, because they're mostly in the direction of the sun when they're observable. We need to go to space and build a telescope. We call it the NEO Surveyor, and we're making progress on it, but it took quite a while to get to that. So the investments in that are substantial, between kind of the order of $1 billion. It just takes a while to get everybody in agreement with that. But that's what it takes to do that.
How much lead time do you need, right? Because you're trying to make small alterations in the orbit of this asteroid. So obviously the more lead time, the better. But what's your expected lead time? How many months or years in advance are you detecting these asteroids?
The type of collision maneuver, bumping a body out of the way, that is of the order 140 meters, 140 yards across, kind of, again, football stadium size. To do that, we, with the power that we're figuring out, perhaps 5 to 20 years. It all depends on the details, right? How is it going to hit the Earth? Is it central, right, to this area? Is it coming in kind of more tangential? It depends, and how big is it really? It also turns out that one more characteristic that's really hard to decide from afar is, what is it made out of? Is it more a gravel pit, or is it more a single rock, right? that depends, right? You need more punch if you put a single rock out of the way, for reasons we can talk later.
Now, people would ask the question of, why is it better to deflect than to just explode the asteroid?
So what really happens if you're exploding the asteroid, and imagine kind of a big project, right? Kind of really scale of, civilization scale, but also kind of regional scale. If you can deflect it, you actively avoid all of the negative impacts that come from that project, right? So you have it kind of a slight bump will hit the Earth as a whole, and therefore there's really nothing bad that happens. If you blow it up, what happens is that the vast majority of the mass that came is still hitting the Earth atmosphere. Some of the pieces may be big enough that they themselves actually create their sub-regional impacts and take not one city out, but multiple cities. But the other ones may evaporate in the atmosphere and create kind of longer term kind of radiation type of changes. Kind of the solar light may not get through. So it's just much better to deflect because it solves the whole problem. In some cases where kind of blowing up may be the only option for that small enough size, it may still be better than just hitting it entirely, but deflection is always better if you can do it.
Now let's talk about the science and the engineering behind it, because it's so high level. You are precisely colliding two objects that are each doing roughly 14,000 miles an hour. Just talk about the level of precision that it takes to make this collision happen.
Yeah, so when everything was said and done with the target, we were 15 meters away from the center. So talking about the hole-in-one, it's not the hole-in-one down a 5-part course. It's a hole-in-one kind of on the other side of the Earth, right? Kind of right in the middle. And of course, what you have not mentioned, but let me mention it quickly: light to get to the Didymus, right? Kind of the parent body or the amorphous that we hit. In fact, took 38 seconds to go up there and come back. And so basically the 38-second, that basically tells you can't joystick it. So you cannot have kind of, like the computer game version, right? In which you kind of steer it into the target. If you want, not only do you have to hit it accurately, by the way, nobody had ever seen the target before, 70 minutes before we were kind of seeing it for the first time in a camera that we carried on the spacecraft. But the spacecraft really has to steer itself into the target. So it has to kind of move and kind of in a complex kind of way, kind of visually identify, center, but then move with its own propulsion system into the target. So I just want to tell you, I couldn't be more proud of the team that did that. Both taught the spacecraft how to do that, but then of course, as always in sports, you only know on Sunday how well your football team is doing in a Sunday game, right? On the field, this team was excellent and really hit it right down the middle.
And you guys didn't even know the shape, right? I mean, this is, you know where it's moving, but you don't even know if it's long or wide, or you have no idea. So how did you calculate that, not knowing the shape? You just aim for the center of gravity, I'm assuming?
Yeah, so what you do is like what the software did, right? The autonomous software. It looked at the shape as it got closer and basically made decisions. So that the software had been trained on many, many different shapes and kind of learned what to do. And what it figured out, the spacecraft, is where the center of mass is as fast as it could. Now, it really was so much easier, kind of this kind of well-shaped potato as opposed to kind of shapes you and I could come up with, like donuts or, like more like barbells, kind of it would have been harder, but the spacecraft was ready to make all kinds of decisions and perform beautifully, kind of finding that center right down the middle.
And, now that we've discussed how much precision and high level engineering went into it, what's the ballpark budget for a project of this magnitude?
Yeah, so we delivered the spacecraft, including the launch and everything from scratch, and including 5 new technologies that we built for the first time, including an ion engine and novel solar panels. We did all of that for $1/3 billion. So you can say, is that big or is that small? Let me just tell you, most missions that you've heard of, including some of the missions on Mars, some in orbit around asteroids, they tend to be much more expensive, right? So kind of the Lucy mission that's going to fly by the Earth later in October is closer to $1 billion, 3 times this. So it will visit, exciting mission, but it will visit, 7 or so asteroids that we've never seen, or only kind of as a dot in some telescope, kind of in areas that we've never observed. In this case, kind of out there at Jupiter distances, but again, close to $1 billion in cost. So this is 1/3 in round numbers of Lucy.
Yeah, I mean, again, like you said, people may think that that's a lot of money, and it is, but considering the precision, the man hours, the technology, the engineering, that actually sounds like you guys got a real bargain. How did you pick the target asteroid, and how did you pick the projectile that you were going to use to hit it? Obviously, so many different asteroids out there, so many different potential projectiles. How did you pick those two?
So first and foremost, I just want to give credit to Andy Chen, who came up with that idea. Let me just explain how he did it. And, it was just a really good insight. So kind of hitting an asteroid is one thing, right? Kind of hitting an asteroid. But to basically be sure that we know how much we bumped it, how much did it actually change its trajectory? It's really hard to do against the night sky with an asteroid that's flying at 30 kilometers per second. That is what the Earth speed is. So kind of that kilometers per second speeds are just really, really, of course. So if it went 10 meters per second or 50 meters per second in a different direction, measuring that against the night sky is really at the edge of what we can do, right? So what Andy Chen figured out is like, wait, if we hit a system where a rock, by the way, 15-20% of all asteroids are dual systems. So they're not just one rock, they're a rock are going around the other rock. And so he basically figured out if we do that, and we have one in which we can measure the orbit really well, we can measure what the impact is of that bump so much better because we see it in the gravitational field, in the force that's from that asteroid, not the sun. And so basically, it just turns out this system in the middle is Didymos. Dimorphos is the one we hit. So the Didymos is like 5 times bigger than Dimorphos. So that was found, and Andy was the guy who identified it. Then the only question is, how do you hit it? How do you get there? And it took 10 months, of course, so that's achievable, right? If it took like 3 years, it's like, wow, that's a much harder spacecraft. So it just really was a great choice. And again, Andy should be credited.
Now, I think people don't realize that, again, you're hitting a building with a much smaller projectile, and it's veering by just, a small percentage, but then over time that leads to it not hitting the Earth. At this point in time, what can we glean from the collision? Was it a success? And did we skew the asteroid enough so that in a real world situation, it would miss the Earth?
So the good news is what we have observed from the ground. And remember, I told you from the beginning that kind of ground observation of the orbit of that system before and after, they happen from the ground. And that's the beauty. Again, we don't need to build a special spacecraft with laser ranging to do that, which surely is another, a fraction of $1 billion or even above, right? So we can use it from the ground. So what we've seen from the ground within minutes, frankly, of the hit is that it was observable from the ground. So it was observable from the ground, first kind of as an initial almost blast, which may or may not have been the fuel that was on board that kind of Wending machine-sized spacecraft as it hit. It could be another kind of, releasing of kind of gas in the asteroid as you bump into it. So we saw that. Then we also saw both with a small spacecraft that was brought up there, kind of that flew with DART, just for the impact. Italian built small spacecraft. And then also from the ground with other spacecraft, including telescopes on Mauna Kea in Hawaii, we saw that there's quite a lot of dust that came out. Now that's good news. When it comes to asteroids, dust is what it is. So kind of just imagine that if you had a rock and you basically had a big cave and the spacecraft just went into that cave and pushed its entire energy, its entire translational energy, its kinetic energy would be deposited and transmitted to that body. If, however, you hit a gravel pit, the spacecraft still deposits its whole energy, but what happens in the front, rocks get blown off and kind of dust gets blown off. And think of that almost like it jumping off the asteroid in the other direction, which is another way of saying there's more force that pushes it. So it's an amplifier of force. Now, this interview, if you want, Doc, is just a few days perhaps too early. So we actually have not completed the full analysis. So just in the near future, you should see news both from NASA and the Italian Space Agency about really what the impact was. But I just want to tell you, looking with my eyes, it's like, wow, this has had the impact that we were hoping for. So I'm keeping my fingers crossed, and I'm waiting for the teams to finish their analysis. It certainly is a success in every other way already. So it is a success because we hit it. It is a success because the Italians imaged it, and we imaged it from the ground. So the final box we'd like to check is to make sure that it's a success and that orbit duration, which is near 12 hours, has been shortened by at least 1.5 minutes all the way up to 10 or even more, depending on how big the ejection was.
Now, you keep mentioning other countries, which is great, because I think people need to understand that this is not just the United States. This is multi-country collaboration. Who are some of the big contributors to this DART mission that you guys have been working with?
The most important contributor here was the Italian Space Agency, Italy. And frankly, I remember I was there, at the beginning. I basically said, look, we're going to bump this spacecraft into the asteroid. I'd like to see it. Can we build a spacecraft? And this was just at the beginning of this kind of small spacecraft revolution that really has been occurring. We have in our portfolio close to 100 small spacecraft. When I started, we had a handful. And so basically, and by the way, it's not just us. There's companies out there, other government agencies are using them. So it's like, let's try with a small spacecraft. And the team immediately reminded me how hard it's going to be. And I said, it doesn't matter, let's try. And the Italians have already released the first images, which shows that there's matter being ejected from there. And frankly, we're still downloading. We have roughly half the pictures down, and so we're still downloading, really pulling that story together. So the Italians are really the most important part. Again, we talked about other ground-based observatories. There's, when everything is said and done, perhaps 20 of those in many different countries on many continents that have been part of this. So my gratitude to them.
Now, let's talk about how does this DART mission dovetail with Space Force, which is the newest military branch?
So, when it comes to the DART mission, it really is at that interface between fundamental science and, in fact, kind of the application, kind of defending, if you want, against threats. And we tend to be in the business of fundamental science, and that's what we're doing. And frankly, just to amplify that point, in a few years, the European Space Agency is going to launch a spacecraft called Hera that's going to go orbit this asteroid we hit, and it's going to image the environment so we can actually see the perturbation we did, because on a fundamental science level, we want to connect those. What is the impact with what are the characteristics of the asteroid, and how we predict kind of whether it's a gravel pit on a rock from afar, because it makes such a difference. In the long term, I think it's a high-level government decision, like who's doing this kind of stuff, right? Should it be the Space Force? Should it be, who should it be? We tend to not be, generally speaking, an operational agency. So far, the defense office at NASA has some operational roles at NASA, but that's a real anomaly. And it's certainly also because it's such a new field. So I think there's a discussion that needs to be had, and probably at the pay level that's higher than you have in this discussion.
Yeah, for sure. I mean, I would say the real question at this point is, what are the next steps, right? Like, this was the initial DART mission, clearly a success off the bat. We'll know more down the line, but what are the next steps? Future missions, funding, what do you envision?
So the next mission is the one I already mentioned, which is Neo-Surveyor, that we hope later this decade we can launch and really go image and get to that congressional limit in the next, during its orbit. So we have 90% of these kind of regional catastrophe bodies discovered. The question really is, should we worry now? At this moment in time, I just want to reassure all of the listeners that we don't know of a single object that will hit within the next 100 years. So it's not something that you should lose sleep over right now. But we want to make sure that there's not of that. More than half that we haven't observed that there's one of them is in fact on collision course. So that's really the next box we need to check. We're going to also focus on some others, really learning how to image, perhaps be more responsive. How quickly can we do a space flight? So this is the kind of stuff that we will focus on. And I think there's going to be a government-wide discussion as to how this is really addressed. And needless to say, if there is something inbound, the whole government comes together. And frankly, we've had exercises, with FEMA and other, including the Space Force, other elements that need to be here because it becomes a matter of security for so many Americans and also people abroad if it hits there.
Listen, Thomas, thank you so much for your time. It's always a pleasure speaking with you. What an incredible interview to see stuff that's in the movies. People think it's science fiction, Armageddon, blowing up asteroids, when in reality, it really could happen, and it will happen at some point. So the fact that you guys are really developing this technology, the advanced engineering, really mind-blowing. So congrats to all your work. You obviously have an amazing team around you. So thanks again for your time, your efforts, and for joining us today.
Yeah, appreciate it. And you're right. When it comes to planetary defense, it's not a matter of if, but when. So we better be ready, right? So the difference between us and the dinosaurs is we can do something about it. So let's really appreciate it. Thank you much.
All right, Thomas. Thanks for saving the human race. We'll talk soon.
Thanks. Bye-bye. Bye-bye.
Take care.